I'm the man on the silver mountain. Okay, we're taking a look here at vertical motions and equations. Now, if you haven't watched the vertical motion intro video or the intro to vertical motion, you need to go do that. There are topics that I talk about in that video that are critical to understanding what we're going to be doing in these upcoming problems. There are a lot of items and values that are hidden information in physics. The values are known, we know how to think about them, but they're not given to us explicitly in our problems and in what we're going to be solving for. You have to be thinking as a physicist in order to use those values, such as the value at maximum height, the value whenever you come back to the ground. Do you have symmetry in your times? You need to go watch that video. If you skipped it, pause this, open up a new tab, go watch it, okay? But if you watch that, you should remember some things, same velocities, different directions at the same height given a symmetric shape. Max height, we have 0 velocity, 0 speed there. Accelerations from gravity is always there at 9.8, negative if we're saying down is negative like we're doing in this picture, okay? So what we're going to do here is we're going to look at how we can have a non-uniform motion, just like we did in the mouse cart problem a few videos ago, but with things moving vertically, okay, being influenced by gravity. So let's take a look at this. We've got a hot air balloon and it's rising straight upward with a constant speed of 6.5 meters per second. When the basket of the balloon is 20 meters above the ground, a bag of sand tied to the basket comes loose. We are asked how long, so what time, is the bag of sand in the air before it hits the ground. Now, great grandpappy Botzer always taught me to draw a picture. Doesn't have to be a good picture, but you need to draw one. So here's the ground. Here is my hot air balloon. I don't know, I guess that's a balloon. And here is a bag of sand on the bottom of it, okay? And all of this is 20 meters above the ground. Now, there's a few other values we know. We know that this balloon with the bag of sand is moving with some initial velocity of 6.5 meters per second. And we also know the value of gravity. We know acceleration is gravity, which in this case, if up is positive according to the 6.5, our gravity needs to be a negative 9.8 meters per second squared, okay? Now, if we want to figure out how long that bag of sand is in the air before it hits the ground, we need to go ahead and find a time here. Now, the first thing I'd like to point out is in this picture. A lot of students think that whenever this bag of sand slips off, its rope is cut, it falls off, whatever, a lot of students believe that this bag of sand will just fall straight towards the ground. That's not true. That is not true, okay? The reason why it's not true is because this entire air balloon with the bag of sand is moving upwards initially at 6.5 meters per second. When this bag of sand slips free, it's actually gonna drift up a little bit and then fall down. And it's not going to arc out, but it's going to have that look to it, okay? It's going to go up in the air just a little bit higher, and then it's going to fall back down and hit the ground, okay? And it's going to hit with some final velocity, which isn't 0. It will have some speed there, but it will go up a little bit higher. So let's just start off by figuring out how long is this bag in the air, okay? So if we want to do this, we can take a look at what we have. We have a VI, we've got an A, which is G, and we've got this 20 meters here, which is technically a delta X. And we'll have to be careful with this 20 meters in a second, but for right now, let's just take a look at what we have. We've got VIs, so here are all our VIs. We've got A's, and we've got delta X's. And we're looking for T's. Oh boy. We're looking for T's. I've got a bad feeling about this. Okay, well, it is what it is. We need to solve with a quadratic here. We have to solve with a quadratic. It is what it is. So let's set this up. Let's just set up the equation first, and then we'll go ahead and move things around to set up that quadratic. So if I want to set this up, I'm going to have delta x, which is going to be 20, but we're going to come back to that in a second. And that's going to equal vi, which is 6.5, times t, plus 1/2 of the acceleration, which is negative 9.8 meters per second squared, times t squared. And something we need to be careful about here is our bag of sand is falling down. If it's falling down, it's moving the negative direction. It's going to have a negative displacement. This 20 better be a negative. Okay? If you have that as a positive, you're going to get the wrong answer. Now we need to set this up so that everything is equal to 0. So I'm just going to bring the negative 20 over to the other side and then kind of rewrite this and make it look more quadratic-y. So the 1/2 in negative 9.8 is negative 4.9 t squared plus 6.5 t plus, because I brought it over to the other side, 20 equals 0. And now I have a value for a, the negative 4.9, b, the 6.5, and c, which is the 20. If we wanted to go ahead and do this with a quadratic equation, we could. That's going to be negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And if you're one of my old students, you would remember that. And that will solve us for the time here. Now, if you're looking at this and you're like, oh, I don't want to solve this right now, Mr. Bosser, please stop. If you actually go back to our very first video with the equation picker, this was example number 8. We've already solved this quadratic. So we're saving us a little bit of time here. If you go back and you check that out, you will see that the time we solved for it, there were 2 of them. One was a negative 1.46 and the other one was a positive 2.78. And in that video, these are both seconds, we talk about how because this is a negative time and you can't go backwards, this time is non-physical, it makes 0 sense, and the 2.78 seconds is what we actually want here. Okay, so we used a quadratic to go ahead and do that. Now, if we want to find what's the greatest height of the bag of sand during its fall to the ground, well, let's go back up to our picture because the picture's super nice. Well, if we look at our bag of sand here, we talked about a moment ago that the bag of sand is going to be moving up a little bit. It's going to go up, and then it's going to fall down. So there's actually going to be this extra little delta h, or this little delta x, right here. It's this little extra displacement given, okay? So we need to look at what that is, and then we can add it to the 20 we had that's beneath it, because we're, 20 meters in the air, and then this little bit extra. So how can we find what that little bit extra is? Well, if we're taking a look at this, and let's kind of zoom in on this, let's make a new picture over here. If this is where the bag of sand starts, and it has an initial velocity of 6.5, we know gravity is always there at negative 9.8. What's going to happen to this bag? This bag of sand is going to move up to some maximum height, and then it's going to fall down, down, down. We know when it gets to its max height, the final velocity is 0. That's where it floats. It hovers for an instant of time. So we have a third thing here. Now we can go ahead and find this delta x, this displacement in this vertical direction. Some people might call that a delta y because it's moving up and down. Really, as long as you know it's a displacement, doesn't matter what you call it, okay? But we do have, in this case, 1, 2, and then the hidden third thing here so that we can solve for delta x. And we just need to choose the right equation for that. And in this case, the equations are pretty straightforward here on what we want. There's only one equation that we have that has 4 things in it without having time, and that is equation number 6. So we're going to go ahead and use that to solve. So let's pull it down over here. For equation 6, we're going to have the final velocity squared, which is 0 squared, and that equals the, well, here, let's do this first. Let's set up the equation and then put numbers in, because numbers can be annoying. So it's going to be vf squared equals vi squared plus 2a delta x. So let's solve this for delta x first, that extra distance, and then figure this out. So to do this, I need to subtract the vi squared. So I'm going to have vf squared minus vi squared equals 2a delta x. And now I need to get rid of the 2a. And since those are all multiplied, I can divide by that. And I just want to be careful here because this VF squared and VI squared, that needs to happen before I do the division. So that's going to be my equation. And now if I want to just start plugging in numbers, I'm going to have 0 squared minus the initial velocity, 6.5 squared, divided by 2 times gravity, which was the acceleration of negative 9.8. And that will give me my delta x. If we run this through, so 6.5 squared is 42.25, and that's going to be a negative quantity, so negative 42.25. We're going to divide that by 2 and divide that by negative 9.8. That will turn things back into a positive, which is nice because this bag needs to go up in the air a little bit. And we're going to see that the bag gains an extra 2.15 meters. But please recall that that 2.15 meters, that's only this tiny little bit of extra here. Okay, that's only the tiny extra. If we want what the problem's asking for, what's the greatest height of the bag of sand, that greatest height is with respect to the ground. So we would just simply add 20 meters to this, and we'd find that this value would be 22.15 meters above the ground. Okay? So that's it. Once again, we're just using more of our best friend. We're kind of analyzing a problem. We did have to find some hidden information here with that VF equaling 0. And down here, we had to do a quadratic, but luckily we had already done it in the past. Okay, so nothing too crazy. The picture really helped us out, so make sure you're making my grandpa proud by drawing pictures like this and using your best friend, because it will always help you out in these type of problems. And with that, our first venture into vertical motion is finished. Y'all try some of those practice problems and take it easy. Adios.